Why? Because why Q is good? Because
We cannot
you can answer some questions, okay? But it's not good enough. Why? Because there are questions which this can't answer actually, okay? And what the picture that we got basically after understanding Q fully is that Q is it's not a kind of continuous line, but it's kind of so if you have integers,
Yes.
0, -1, -2, 2 and so on and so forth, then Q are it's like Q something like that. Okay? But this line is not a continuous line. So there are gaps in it. And why there are gaps in it? That, for example, if I take a number, okay, which is constructible number, it does not lie on any of basically these rational numbers. So it's like if I take 1 and 1, okay, then the length of this hypotenuse of this right angle triangle is not going to lie on any of the points of QI. Okay. So in other words, there is going to be some gaps actually. Okay. Very specifically where this gap is going to be somewhere, afterwards, after the one actually. It's like you have a hole. Okay. And next thing that we would like to do, we will discuss basically, and I would like to quickly recall, is that how you can fill the gaps. And in order to fill the gaps, we are basically introducing some new notions, and those notions are Dedikind cuts. Okay? Now, what's a Dedikind cut? Quickly. So alpha is a Dedikind cut. Obviously it's a subset of Q. Is a Dedikind, maybe alpha is a cut specifically if alpha is non-trivial. In other words, it's not anything.
It is not nothing.
It's not nothing and it's not everything. Okay?
Yes.
It's not everything. Okay, it's something actually. And the second condition was that alpha must be closed downward. In other words, if you take any P from alpha and you take a Q from Q with property that Q is less than P, then Q must belong to alpha. In other words, what we are saying, that if you pick an arbitrary point P from alpha, for example, if I say that that's a cut, okay, and the cut is set of all rational numbers which are basically on the left of this cut, okay, and then it can't be the whole rational line, and there are some points obviously there, okay, so that's kind of non-triviality. And then if you pick any point P from this cut and you take any other point Q from rational line which lies on the left of the P, okay, then that Q must be part of the same cut actually, okay, and that's something that we call that it should be closed down. We discussed this in detail last time, okay, so I'm just giving a kind of a quick recap. And what was the third thing that it must have? Yes, there is no greatest element here. In other words, if you give me a P in this alpha, there will be always a rational number Q which is going to be bigger than this P. In other words, for for any p in alpha, you know, there is q in alpha such that p is less than this q. Okay? So in other words, you can always find basically
There is no
there is no supremum. There may be a supremum. I mean, so we don't have a trouble with supremum. But we are saying that within set there is no greatest element actually. You pick any number, you can always find a new number which is going to be bigger than your.
If there is a supremum, it won't be in the set.
But it may be in the set. You know, fine. I mean, if you.
So you will have a greatest element in the set.
It's a good point. Yes, it's a good point. It's a good point. That if we have a supremum, then it should not be in the set. Thanks for this point. Yes, I mean, then you will have basically greatest element. So supremum may exist. May exist not in Q,
not in alpha.
but in some other form. Okay, whatever that form is, we're gonna see that. Okay, and then we saw that there are some examples of the cuts. Okay, and we discussed in detail that why these examples are basically cuts. So alpha, if you take a alpha as any finite set, it's like -3, -4, -5, and -5, something like that. Okay, so it's like you have just a finite set. Now, can this be a cut? So it can't be a cut actually.
Second one.
Okay, and then if you take this set as a the key set actually, which kind of forced us to think about the gaps and forced us to think about that how to fill the gaps, was what? That so alpha is a collection of those rational numbers for which x square is less than 2. So that's not either a cut actually, okay? So that's not either a cut. Why it's not a cut? Why it's not
Because
a
we
cut?
can find Q and Q.
It's not closed downwards.
It's not closed down. Okay? It's not closed down. That's a second example. So that's not a cut, that's not a cut. So what was the example of a cut that basically we? So examples of cut was, for example, you take the set of negative rational numbers. In other words, you take those rational numbers which are less than 0, and that was, we saw actually that was a cut actually. Okay, it's closed downward and there is no greatest element in it, then obviously it's not empty and it's not everything.
Sir,
Uh-huh.
can you explain the second property in example number 1?
Uh-huh. Hey, okay.
Close
Sure.
downward.
So it's like if you take a finite set, a finite subset of a rational number, it may or may not be, it's not necessarily going to be basically cut. Why second property is not true? Just think about it. I'm taking a rational number, -3. Can you tell me a rational number, smaller than -3?
Yes.
There can be lots. For example, you take -7. So is -7 here?
No, sir. We can.
It's not here actually. Okay? So the -7 is not here. It's not a cut actually.
Sir,
Uh-huh.
can we have example of finite set to be a cut?
So I guess that you can demonstrate in general that not every finite set can be a cut.
Yes, sir. We can.
Okay? It's not going to be closed downward. Okay? And if it is a finite set, then there must be a greatest element in it. That's another trouble.
Yes, sir.
Okay? So it avoids basically second and third both.
The third and second.
सर
Okay?
हमने एक और बात देखी कि अगर हम पॉजिटिव रेशनल नंबर
हम्म।
लें तो वो भी एक कट बन सकता है।
नहीं।
अगर ये हम दोनों प्रॉपर्टी
if we define them opposite
Close
actually.
downward, upward करें और तो sir
We have to just agree on one definition. Okay? We just define that what's a cut. So if you define cut to be this way, then set of positive rational numbers is not a cut. Okay? How about if I take alpha to be z? Is this a cut?
No, sir.
Cut of integers. Is this a cut? Okay, not z. Okay, maybe you say that, so obviously it's not a, some good coordinate. How about if I say negative integers? So that's negative integers. Why the trouble in it?
It has the greatest element.
It has the greatest element, and if this second property is true in this case,
No,
it's
sir. That also was-
not also violated. Okay? Violates second property. But why it violates second property?
Sir,
What's the second property? Second property says that you take something from your cut, potential cut, candidate of cut, okay, and you take something from rational number which is smaller than cut. Then that smaller thing should also be part of the cut. So tell me something that why this is not a good candidate for cut. Why second property is not satisfied here?
it's integer.
Uh-huh. Now just give me a concrete example. Uh-huh. You take minus 1/2. It's rational.
Argue to be minus 1.
Not it.
Okay.
Yes.
It's smaller than minus 1, for example. Also, it's bigger than minus 1. Okay. So we need to take something else. So let's 3/2.
3
Let's take minus 3/2. Okay. So the minus 3/2 is not here. And hence it's not a cut. Okay. So you can have
We can have any rational number that is not integer. Any rational number bigger than, lesser than minus 1.
But you can
It's
have
not
a cut.
integer.
So say for example, if I say that, okay, that's not a cut, but what if I define this to be a cut? So I say that 1 is a set of rational numbers which are smaller than 1. Is this a cut? Would that be a cut? So it's like, cutting the rational line, okay,
Yes.
at 1 line. Is this a cut?
Yes, sir.
So there is no greatest element, and it's closed downward, and it's non-trivial. It's non-trivial. Okay? So you have non-triviality as well. Alright, so you can have lots of examples basically, and non-examples for that.
वन की जगह पे कोई भी
कोई भी ले लें, that's going to work. That's going to work. ठीक? Even you can take some rational actually. You can take a rational. So it's like you take the set of all rationals below some rational.
And if we put, sir, less than or equal to 1.
No, obviously then you have a greatest element. And the greatest element is going to be something which is troublemaking. Okay? So we define cuts, we know some examples of cuts, we know some non-examples of cuts, and it's quite important to know the non-examples. Okay? Your understanding boosts 100% when you see the non-examples. Okay, examples are important, but non-examples are even more important. So always look for non-examples. Okay, something which does not satisfy your required property. Okay, so next we are defining something which is called a real number, a set of a real line, okay, or this strange creature, and we say that if you collect all cuts where alpha is a Dedikind cut, okay. Then, so in other words, I'm defining this creature R, okay, as the set of all Dedikind cuts. Okay? And I'm going to show actually afterwards that this R corresponds to really our everyday understanding of set of real numbers. Okay? So for mathematical analysts, every real number is not just a number, but it's a Dedikind cut. It's a set actually. Okay? And my claim is that this alpha or this collection is going to basically fill all gaps. Okay? So we also wrote a theorem. So I'm just quickly recalling what we discussed in detail last time. Okay, I want to go ahead with the next part. So what was the meta theorem that we did? It's kind of a, it's in principles, it's theorem 1.19. Okay, and its proof is in appendix. It's a bit tedious. Okay, it's bit involved. So I always say that, don't die before doing this theorem at least once in life. Okay? So it's like, maybe you have to answer a master math petition in the day of the judgment that why you haven't done the proof of this theorem. Okay? Get prepared for that. So at least you should do that. Okay? So what we are going to do next is basically this theorem. So what we are going to do, we are going to define a notion of addition and multiplication on this R. Okay? And obviously we'll also define a notion of order. And we are going to show that this set with these operations is an ordered field. Okay? Is an ordered field. So it satisfies the field properties. Okay? And what is the second thing, that key thing that we want to do? That we want to show, or will be showing, that when we are actually defining this R, we haven't lost Q. So the Q is already there. So in other words, we need to show
Q is
and
embedded in all.
so we will also show that Q is embedded in R. I hope that now you understand this is simple, that Q is embedded in R as a subfield. If R is a field, then Q is a subfield. Sitting silently in this R. Okay? Moreover, we would like to prove that this R has what you call the least upper bound property. Not only least upper bound property, but completeness property, greatest lower bound property as well. So I'm just going to focus on least upper bound property because the greatest lower bound property is going to be very much analog to what we are doing here. Okay? And what was the least upper bound property? What was the least upper bound property? So what was the property which says that if you have an ordered set, so you have an ordered set, okay, and
it is a subset which is upper bound.
And E is a subset of S such that E is bounded above. It's bounded above. In other words, there is an upper bound for this A. Okay? Then E has a supreme. Okay? E has a supreme. I mean S within that set S. Okay? Making sense. So in other words, every bounded above subset has a supremum. So in other words, you want to prove a subset of an ordered set has a supremum, you just prove that it's bounded above. Okay? And for the infimum, obviously you need to have the lower bound. Okay? And we have saw this example that this property is not in Q actually. Q is an ordered set, we have ordered there. Okay? But Q has not least upper bound property. Can you give an example where this least upper bound property, what example I can use or counter example I can use to show that Q does not have the least upper bound property? One of the examples is here.
Dedikind cut.
Just think about this example. It's not a cut actually. Okay? So what does this set is saying? So we can demonstrate actually, and if you haven't seen it, then you must see this. So that's really the first example in Rudin book. If you see, I guess that example 1.1 or something like that, where he proves that this set do not have, so it's bounded above, obviously there are upper bounds. So what are going to be the upper bound for this set? So the obvious one is 2. 2 is an upper bound for this set. Okay? But this does not have a supremum in Q actually. There is no supremum in Q for this set. That we can prove actually. In other words, you can basically show that it's not possible to find a supremum for this. So though this set is bounded above in Q, but you can't find a supremum of this set. Okay? And you can see that Rudin, I guess that example 1.1 actually. It's really the first example that it shows. Okay? So this least upper bound property is not everywhere. Okay? So we're going to show that it's in R actually. It's in R. In other words, if you take any subset of R which is bounded above, it is going to have a supremum. It's going to have a least upper bound. That's what the next the key objective that we want to have. And hence we say that in this sense that R is complete actually. There are no gaps. In other words, so if I have this cut, okay, why I can't find kind of a supremum here, okay? So in other words, why I can't find a supremum here actually? For that you need to see proof. Obviously, I will highly encourage to go through the proof, okay? But what we are going to see that since this set, okay, is bounded above, okay, so there are lots of bounds for this, okay, in R, okay, then we can treat actually that this gap as the supremum of all these numbers which are, you have here. You just take their supremum and you say that this supremum is going to be something that something is
Not in Q.
square root of 2. We're going to name it as square root of 2 actually, and hence that square root of 2 is going to fill this gap actually, which was left behind by Q. Okay? And it's just coming due to the least upper bound property. So what's a least upper bound property? Simply, you take a subset with upper bound, there must be a supremum. Okay.
That's it.
In that set, within that set. So Q do not have a least upper bound property because I'm taking a subset of Q, okay, which has an upper bound like 2, but doesn't have a supremum in Q.
So we are accepting that radical 2 is not a concrete number. As we define radical 2 to be a set, set that x square is less than.
Not set, but as a supremum of a set actually.
Supremum of a set.
Of a bounded above set. Supremum of a set. So it's a concrete number.
But if we go more abstract, then it's also a set.
Huh?
If we go more.
Obviously. You treat that as a cut actually. It's a set. Okay. So that's something boring that we did last time, or at least mentioned last time. And our objective in this class is to basically give a decisive and a conclusive argument on this proposition actually. Okay? As I said, I'm not going to do the complete proof. Okay? For the complete proof, you have to see Rudin. Okay? The proof is in appendix of the first chapter. Okay? It's the end of the first chapter. And let's move ahead. Okay, so from where we should begin? Let's define addition.
Order defined.
Let's even we defined basically order and addition. Defined addition and order. So let's recall it quickly. Okay. Why R is ordered set? R is ordered because
we can define an order with
because if I have a cut, okay, containing lots of rationals, and I have another cut containing other lots of rational numbers, and if this is alpha and this is beta, okay, so in other words, like these two cuts are on the same rational line, so you don't treat that these two are different creatures. So alpha is here and beta is somewhere here. Okay, so we agreed that what should be, let me ask from you again, that what should be the meaning of that a cut being smaller than another cut?
corresponding sets are the sets.
So we said that this is going to be true if and only if
Alpha is subset of beta.
alpha is properly contained. Properly contained. In other words, there must be some element in beta which is not there. Okay, so it's properly contained. And then, the transitivity is very much obvious. Okay, because the containment is transitive. Okay, so alpha is subset of gamma, and a gamma is alpha is subset of beta, and a beta is subset of gamma. Then alpha must be subset of gamma. Transitivity is very much obvious. And we actually also saw why the trichotomy law should be true. Okay? I'm not getting into that again. When you want to see the rule. Okay?
Sir, defining, we had also defined a dictionary order. Is it necessary to define over here? Or
On R, what do you mean by that? So that order was on Q. R is completely different from Q. Okay, it contains Q as a subfield, but it's different from Q. So you can't, take kind of balances that you use to measure, one thing, to compare one thing, and you use the same thing for basically, some other creature. So you need to obviously define a new order. Okay. So let's define a plus actually. Okay. So what we want to do is that, okay, I have this a cut, okay, another cut, which is beta. Then I would like to define that, okay, what should be the meaning of alpha plus beta? What should be the meaning of adding these two subsets of rational numbers? So what should be the meaning of adding two subsets of rational numbers?
like every element of alpha and every element.
So it's like you take all possible pairs from here and add them. In other words, alpha plus beta comprises of R plus S such that R is in alpha and S is in beta. So we define that. Okay? But is plus well defined? So what we should do to verify the fact that this addition that we have defined is a well defined basically. What should we do? Uniqueness to prove करनी है. We should show the uniqueness. So it's a kind of uniqueness is pretty much obvious here that okay, you have had two sets and you are getting a set. So it's like, I don't see any trouble with uniqueness. The only thing is going to be that okay, if you are adding two cuts, so you are getting this result. So does this belong to the same family? So in other words, if these two numbers, are real numbers, then this creature that you have defined as basically sum, is that a real number as well? In other words, is this a cut or not? Okay. So why this should be a cut?
If it follows property.
Can you give me a concrete reason, just like a very much concrete reason that why alpha plus beta is not empty and is not everything?
Because alpha is not empty and beta is not empty, so their addition must also be, as we have described.